Today we have Amir.
Nourbakhsh.
Nourbakhsh, thank you.
Sorry, it's hard.
And he's works with Tomas Palacios as a postdoc at MIT. And in the lab, they're doing some of the most impressive things that I've seen with these transition metal dichalcogenides and other types of atomic level systems moving toward real devices that will do something useful like compute and sense and the like. And she's going to tell us about today. Amir did his undergraduate and graduate work at AMEC in Belgium. And I was quite impressed with AMEC. It's like a real serious fab. You know, they actually make chips there. And I gave a talk once following the AMEC talk. And it was such an excellent talk that the AMEC people gave that I was humbled. And but I was really impressed that they're really spun up all the way, and they're, at the same time they look at things like that.
So thank you very much for the introduction. It's great to be here. Hello, everybody. So actually today I'm going to talk about 2D material-based transistors. That's what this title means. We want to see what are the advantages of this new class of material over conventional semiconductors, and whether we can use them in next generation of transistor, and if so, when and where that would happen. That's a very important question because right now, mainstream industry, electronic industry, is very seriously looking for new options to replace conventional semiconductors such as silicon, because it's been working for about 50 years, and it's right now, silicon transistors are very small, and silicon is very close to its physical limit. So it's time to replace it. So everything is about digital electronics, which we all know how has changed our life. Wherever that there is some interface between human and some sort of machines, there are some electronics integrated systems in between. I was in a seminar actually this morning, and I heard that number of cell phone subscriptions, connections, has reached to 6.8 billion connections now, which is about, I mean, world population. And they expected that in 2 years that actually would exceed human populations. So that simply means that anybody who is capable to operate a cell phone now has a cell phone. And it comes in different forms. I mean, it can be a very complex CPU, like what I have here in this laptop, or just a simple processor in this laser pointer that has only two buttons and help me to switch the slides. But it seems that what has been done so far is just the beginning. We are entering the era of Internet of Things, which the idea there is to implement electronic devices, active and passive devices, almost everywhere. Whatever that has some volume should carry some electronics. So these devices would communicate with each other. So they are on the sort of internet network. They collect data from the environment, they analyze it, and then eventually help us, ideally, to have a better life, to optimize several parameters. So the idea is to have smart hospitals, smart highways, so for example, control, optimize the traffic flow, have smart cities, smart factories, almost a smart everything. This is also a scary idea. A lot of people are concerned about the security issues because now we are going to connect everything to internet, and we already have some security issues. So increasing the size of devices connected to internet, that would be a concern. But anyway, what is important for us is that the available hardware electronics, does it have the capability to provide hardware for this growing electronic or not? Or at least we need to make sure that the electronic industry can keep growing in next couple of decades. About the hardware, everything is about integrated circuits, beautiful compact systems that is designed to do certain tasks. These black boxes are full of, if we open them and zoom in, we will find a large number of transistors inside. But actually, we cannot see under a normal optical microscope. We need SEM because the average size of transistor these days is below 100 nanometer in diameter. So for this new technology platform, the Internet of Things that I already explained, we need to make sure that we have high volume and high speed and very cheap, low cost electronics, because we are increasing the amount of electronic devices. And also the power consumption is very important. We don't want to charge electronic devices very often. We already have problems with charging, I don't know, cell phones or laptops. But having electronics everywhere, that requires a very low power systems. So as I said, ICs are made of transistors. And this days, number of them has increased to about 1 billion. I mean, the chips carried in 2012 had about 1.1 billion transistors. Today it's about 1.5, I believe. And by 2018, that would reach to about 3 billion transistors on a CPU area. Right now, we are using MOSFET technology, which is a metal oxide semiconductor field effect transistors. That's the most practical form of transistors. These transistors or MOSFET devices are in principle switches. They act as a switch. They have two states, off and on, corresponding to very low current and very high on current. The device is normally a lightly doped semiconductor channel with two heavily doped source drain area and a gate electrode which is separated by a layer of dielectric from the channel. So it can control electrostatically modulate the barrier between source drain, and by that it can control the carrier flows so that we can switch between on and off state. And when we have a couple of transistors, we can design different logic gates, build circuits, build ICs, and in general, microprocessors. So as you can imagine, the overall performance of this single transistor, the individual transistors, is very crucial to the overall performance of the electronic devices that we build. Well, the MOSFET that I already explained, it's not an ideal transistor. So we don't have such an abrupt transition from off to on. There is a slope here, which at room temperature, the best is 60 millivolt per decade. So we need a substantial gate voltage to switch from off to the on state. And actually, that we need to be careful with the device architecture, because when we scale it down, make the transistor smaller, the slope can actually be worse. That can be easily affected by parasitic short channel effect, so that we need to optimize the device structure in each generation to improve the gate electrostatic control over the channel to have the subthreshold slope close to 60 millivolt per decade. Well, actually, there's a very interesting roadmap here for a number of transistors known as Moore's Law, after Gordon Moore, one of the co-founder of Intel. The roadmap says that the number of transistors has to be double every 2 years on an affordable CPU area. And as you see, that's been pretty successful in the last 50 years. I read somewhere that's been the most successful roadmap that human being has made so far, has achieved so far. When those roadmaps started, the number of transistors were about just a few hundred. And today, as I said, we have more than 1 billion transistors. We just want to make sure that this roadmap can continue, at least for one more decade. So about the device structures, the roadmap is just an economical roadmap. It doesn't tell us how to build this device and what we need to do, how we need to evolve the device structure. In fact, the device architecture has changed a lot since the invention of MOSFET transistor, which was a bulk silicon transistor. Today we have FinFET, which are very narrow layer of silicons in a vertical configuration, so the transistors now are vertical. The oxide has changed. The dielectric material that we are using, it used to be silicon oxide. Today we are using high dielectric metal oxide source drain, gate metal. Everything has changed. The only thing has not changed is the semiconductor material, which is still silicon. So for 50 years, we've been using silicon. It's been such a good material for us. But as I said, silicon has reached to its physical limit, because right now, for a channel length of 15 nanometer, the silicon thickness is about 5 nanometer. The rule of thumb is that the channel thickness has to be about 1/3 of the channel length. And this 5 nanometer down to 4 nanometer, I would say, is really the physical limit of silicon. Going further down, make it thinner, silicon would not behave as a good semiconductor anymore, because the surface states would dominate the performance of the channel, so that the mobility would degrade, and both on current and off current would change, so that the device performance would be very bad. So we need to replace silicon with some other semiconductors. Options are high mobility channel material, such as silicon germanium and germanium as a p-type semiconductor, and the family of 35 semiconductor as an n-type, such as indium gallium arsenide. This material typically have a very high mobility, much higher than silicon, so that basically they can delay this effect that we see in silicon. And that's, well, it's expected that work for maybe 1 or more 2 generation. But since they lattice, the structure of this material is pretty similar to silicon, they are bulk semiconductor, it's been already shown that this new class of material would face the same issues that silicon is facing today. So maybe in a few years, we again have to change them. And there, especially for sub-10 nanometer region, where the channel has to be below 3 nanometer, it seems that the only practical option is 2D material. Or in general, low-dimensional semiconductor, which have a naturally atomically thin body thickness, down to a monolayer, which is sub-nanometer thick. As I said, the main advantage of this material is that, well, the bulk crystal is a layer crystal, so the bonding between layers is just very weak van der Waals forces. And that's why we can thin them down to a monolayer. And that surface doesn't have any dangling bond. Also, as you see in this TM image, they are very uniform. That's a big advantage because technically we can thin down silicon to a few nanometer, but there is always 1 to 2 nanometer roughness. That's not a big deal when we are dealing with a 10 nanometer film, but in a 3 nanometer film, 1 nanometer is about 30% variation, and that induces a huge device-to-device variation. But in this class of material, the thickness is very uniform, and that's a big advantage here. About mobility, which is very crucial in device performance, well, as you see in this graph, even high mobility semiconductors, such as indium gallium arsenide or indium arsenide, they lose mobility when we scale down the channel to a few nanometer. Actually, in indium gallium arsenide, the mobility goes below 100 square centimeter per wall second if it is thinned down to just 3 nanometer. And if we continue that, well, I would say at 1 nanometer, we will not be able to measure any measurable mobility. But in typical 2D material, like molybdenum disulfide, in general layer semiconductors, well, we have already very low mobility, maybe just a few hundred square centimeter per wall second, but this is much less sensitive to body thickness. So that is almost, we still have some variation, but it is almost preserved. So in a high quality monolayer or a few layer of tungsten cyanide molybdenum disulfide, we can measure mobility up to 100 or 200 square centimeter per wall second, which is way above what we can measure in conventional semiconductor with the same thickness. So transition metal decalculated family, it's a rich family of semiconductors. We have both p-type and n-type semiconductors, perfect for CMOS application, different energy band gaps, different electron mobilities. Here in this work, we are using molybdenum disulfide, which has a large band gap and a very high effective mass of about 0.45 electron mass, and a low dielectric constant of about 4 to 7, depending on the number of layers. These properties are perfect for low power application because large band gap and high effective bands would lower the contact, the off current in the transistors. Especially the high effective mass basically suppress direct source drain tunneling. And the low dielectric constant help us to further improve the gate electrostatic control over the channel. MOSFET is an n-type semiconductor with a very low off current in transistors. The off current typically in long channel is below 100 femton per micrometer. The subthreshold slope is about 70 to 70 millivolt per decade. And so as you see, we have very large on-off ratio, a good transistor. Also, MOS2 forms a very good interface with dielectrics. So that we, as you can see here in the CV characteristic, we have a very good transition from depletion to the accumulation mode. Please.
I think because it's impressive performance. What do you do about the surfaces? Does it have, is it on a substrate? You've got an overlayer on it?
Well, the device structure is like this. We use highly doped silicon as a backgate, and then we have a thin layer of hafnium oxide as the backgate. We transfer the channel, and we have this isolation layer, thick silicon oxide as an isolation layer, so that basically separate the measurement pad from the gate. So that's why that you probably will not see it because the substrate is very shiny.
No, but if I was to
Yeah. So, but now the question is that can we really scale it down to sub 10 nanometer or not? So this graph shows us the minimum channel length of a transistor versus semiconductor thickness as in benchmarking silicon nanowire structure, which has the best electrostatic, this is the best silicon transistor we can build, and planar molybdenum disulfide transistor. As you see, to have a channel length of about 6 nanometer, we need about 3 nanometer of silicon. So the diameter of nanowire has to be about 3 nanometer, which, as I said, is really the physical limit. It's already beyond the limit of silicon. But this point is actually a beginning for molybdenum disulfide, because 3 nanometer MOS2 is about 3 layers. It's 4 layers molybdenum disulfide. And we can further scale it down to a monolayer, which theoretically would give us a channel length of 3 nanometer. That's very fascinating. However, there's an assumption behind these numbers. These are just the theoretical calculation. The assumption is that basically the lateral source draining electric field is 100% confined in the channel, so that the source draining electrodes are thin enough so that all the electric field are going through the channel, not through the oxide or the surrounding. That's very important. It's not a big deal in long channel transistors. We can use very thick metal layer as source draining contact. But in short channel transistor, in this dimension, we have to add some access region, ultra thin access region, to contact the 2D channel. So the idea is that if you are using a 2D channel, the contact should be also 2D metal, or at least a very immediate contact. So that was the first demo that we work on it. If you are working in a 2D material lab, graphene would be the first options that you would think about it. It's very conductive. It's only 1 atom thick, so it is even thinner than MOS2, which is 3 atom thick. And for engineers, graphene is just a metallic membrane. For physicists, it's much fancier. It's a gapless semiconductor, or it's a semi-metal. But yeah, we cannot deplete it, so it's always on. I mean, the resistance is the sheet resistance is relatively low. So this is the device structure that we designed. We have 2 layers of graphene with, as a source drain. We have a trench here that defines the channel length. You see it here in these AFM images. This is a typical process flow. We first stack a layer of graphene and molybdenum disulfide on a p-type silicon wafer with about 10 nanometer hafnium oxide as the gate dielectric. Then we selectively etch graphene to define the channel. Finally, we put down the measurement pad, gold layers. And if needed, if we need to improve the electrostatic, gate electrostatic, we can build a top gate electrode as well. So we deposit another layer of hafnium and a top gate metal. So the etching step is very important because that can easily damage the underlying molybdenum disulfide. We want to etch a monolayer of graphene over a monolayer or a few layers of molybdenum disulfide. So we need to be careful with that. Here in this work, we use diluted oxygen plasma with very diluted oxygen. So we dilute it with helium. And then we keep the sample upside down, so it's not directly exposed to oxygen species. And then also we apply just pulses. It's not a continuous exposure. We monitor it with Raman spectroscopy. This is the Raman spectra of S-transfer stack of graphene on MOS2. So you see we have a G peak, very small D peak here. This is a CVD graphene, so it has some small defects. And these peaks are from MOS2. After a couple of pulses, we have a large D peak here. So graphene is fully oxidized. It's still there, but it's oxidized. And then finally, after a couple of more pulses, graphene is completely etched away, but the MOS2 peaks are intact. So that we can very selectively etch graphene over MOS2. Oh, I should apply this. About patterning, for high resolution patterning, we use e-beam lithography. We just developed the PMMA at very low temperatures, minus 15 degrees, to have very sharp features, as you can see here. We could get down to about 10 to 20 nanometer trench width. I don't know if you can see them here. This is graphene after removing the PMMA residual, so that the the pattern are all transferring to graphene. We have 2.5 and 5 nanometer, but as you can see in this schematic, they are not fully developed. So only 10, 15, and 20 nanometer are developed down to graphene. This is the device. Here we see channels, 3 transistors with 60, 30, and 15 nanometer channel lengths. I should mention that the minimum channel lengths that work for us, the patterning basically, was 15 nanometer. Although we can see the 10 nanometer, but it's not fully developed, so it still is some graphene residual there. But 15 nanometer is the minimum that we have right now. So all of them show very low off current, as expected. It's a wide bandgap semiconductor and very linear subthreshold characteristic. But as you see, the 15 and 13 nanometer channel are already affected by the short channel effect. So it's less steep. The swing has increased. So that's we need to improve it by applying the top gate. So we put down the top gate and connect it to the back gate so that this device now is operating in the dual gate configuration. And as you see, the subthreshold slope, now the subthreshold region is much steeper, and the swing has decreased to about 90 millivolt per decade. Here, the off current also decreased to 10 picofarad per micrometer, and we have some improvement in the on current. That's a good device, but as I said, the idea here is to go really down to 10 nanometer and eventually to sub 10 nanometer region. But there are two issues that need to solve before continuing. The first one is that, well, still we are using a top-down approach. We are using lithography so that the resolution is limited. Well, on the device is about 15 nanometer, and our pattern is about 10 to 12 nanometer. But obviously, we cannot go below 10 nanometer using this technique. So that we need a more bottom-up approach, something with nanometer resolution, single-digit resolution. The second problem is that we saw that the contact resistance is relatively high, or the on current is lower than what we expected, at least an order of magnitude. It turns out that it's due to the large series resistance here between graphene and MOS2. Both are 2D materials, so the bonding between them is just weak van der Waals forces. Means that we always have a layer of vacuum in between. So that's a tunneling barrier, and induce an extra contact resistance of about 10 kilo micrometer. So what we learn here is that to lower the contact resistance, well, first, still we need to use a 2D material, but that 2D contact, 2D metal, has to be covalently bonded to the channel. So that this way we can eliminate this barrier. To solve this problem, we use metallic molybdenum disulfide as the contact. So we design a device structure like this. We have a metallic MOS2 as contact, immediate contact, and a semiconducting MOS2 as the as the channel. The good thing here is that we have a seamless junction, so both regions are covalently bonded together, and the mismatch between them is very small. So it's sort of a homojunction. Well, yeah.
How do you make it metallic?
That's what I'm going to explain here. Almost all of this transition metal dechalcogenide have a metallic phase beside their semiconducting phase. And it's relatively easy to switch between these two phases. They're reversible. In case of MOS2, we typically use metal organic compound like N-butyl lithium. We just dip the sample in the solution, keep it for a while, and then rinse it. And then you have the metallic one. To go back to the semiconducting one, you just need to heat it up.
So where does the
Yep.
where does the lithium go? It's a very small atom.
It intercollects, but then we remove it. Actually, we rinse it with solvent, and yeah.
But enough of them stay in there.
Well, and the idea is that ideally we don't need to keep lithium there. So the thing is that when we heavily dope molybdenum disulfide, the semiconducting configuration is not stable anymore. So it naturally undergoes this phase transition. It goes to the metallic one. Now, theoretically, if more than 80% of MOS2 is basically doped, even when we remove the dopant, it remains in its metallic phase because there is a potential barrier between them. It needs enough thermal energy to overcome the barrier. So that's stable at room temperature. You see here peel before and after. Single layer molybdenum disulfide is a direct bandgap semiconductor, so it has a very sharp peel peak. After the phase transition, as you see, the peel is 100% quenched. So that's because the bandgap is closed, and that's what you see also here in this DFT calculation done by my colleagues way here. So the metallic one, the gap is completely closed. So here we can compare metallic and semiconductor MOSFET transistor. By the way, the semiconducting one is labeled 2H, and the metallic one is labeled 1T or 1T prime. So as you see, the 2H one, as expected, it has a very large on-off ratio. It's a semiconductor channel. But after the phase transition, when we have a metallic channel, the current is constant because we cannot deplete it. There's no band gap.
Do you know what the density is?
Density is above 10 to 12 per square centimeter, for sure. So to build a transistor, obviously we need a semiconducting region, so that we first need to protect the semiconducting part, the channel region, before the phase transition. Here in this work, we use PMMA mask. It's a long channel transistor, it's about 400 nanometer here. And then we apply the same phase transition, the chemical treatment. So as you see, after the treatment, we still have a transistor, very large on-off ratio. But as you can see, the current and both the transconductance have improved, so that the junction is good. The series resistance is relatively small. Important point here is that the channel length is equal to the width of this polymer line, so that the width of the polymer is defining the channel length for us here. And to going down to 10 and eventually sub-10 nanometer region, the only thing that we need to do is that to make this polymer line smaller, narrower. But as I said, lithography, E-beam or photolithography would not be an option here. We don't have such a high resolution to build such a small features. So here in this work, we use Block-Copolymer technique, which is a bottom-up approach. Instead of exposing a resist, here we have two distinct polymer. We mix them, and then I spin it on the surface, and then somehow you have the phase separation. It's either by a solvent treatment or a thermal treatment. These two phases separate, and they form a kind of periodic nanostructures. And then eventually we selectively etch one of these blocks. Here in this work, we are using polystyrene and PDMS. Polystyrene is an organic polymer, so that can be easily etched by oxygen plasma. And PDMS is a silicon-based polymer. It's very hard, so that would survive the etchings. The SEM images you see here shows different PDMS lines with pitch 43 here, 18, and 15 nanometer here. So the width of polymer lines is equal to the half pitch. So here in this work, we are using the 15 nanometer, so that the half pitch or the polymer width is about 7.5 nanometer. And that corresponds to the channel length. Well, obviously, for device, we need them sorted parallel together. If there is no feature in the surface, they form such a random morphology. But to have them directed in a self-align, we need templates. Here in this work, we use gold lines, as you can see in this schematic. The reason that we use metal here is that later we can use them as external contact to the MOS2 channel. So it's 2-in-1. It works as the template to have parallel lines. Also later we connect them to the source drain bias. This is the summary of the process flow. We start with depositing CVD, monolayer molybdenum sulfide, or few layer molybdenum disulfide on a half mirror silicon substrate. We put down the metal contacts. We have to functionalize the surface to improve the adhesion of Block-Copolymer to the surface. We deposit and develop Block-Copolymer, and finally we etch the polystyrene line. So we are left with this parallel PDMS line on MOS2. And finally we apply the phase transition that I already explained. That converts the MOS2 channel to a series of metallic semiconducting region in series. So that actually we have a chain of transistors now, which are in series. The semiconducting part are the channel, and the metallic part in between are the interconnects. So here's an example. I have a 2 nanometer thick channel, so it's a tri-layer MOS2 exfoliated one. And we have 6 lines, so 6 transistors in series. This is before and then after the phase transition. So as you can see, we still have very low off current, about 10 picoampere per micrometer, and relatively high on current, about few 100 micron per micrometer. So it's already order of magnitude higher than what we had in our graphene contacted MOS2. And the subthreshold slope is about 120 millivolt per decade, which is excellent subthreshold slope for such highly scaled channel. So Next step is to model them, to extract some of the intrinsic parameters, such as mobility and velocity, also the resistance, the extra resistance that we have in the system. Here in this work, we use the MIT virtual source model developed by a group of Professor Antoniadis at MIT. That's particularly developed for short channel devices, and it already been tested on several semiconductors, silicon, high mobility channel material, and also gallium nitride power devices. But in our case, as I said, we have a chain of transistors with some internal resistance, so that first we need to develop a circuit model to capture all the effect. So we use this simple model. We have n transistors in series with this internal resistance, which represent metallic semiconducting MOS2 junction resistance, and two external resistance, which represent metal MOS2 contact resistance. It's very important for us to know how much, what this resistance is. So here is the fit. I have two examples. This is the tri-layer result that we already saw, and this is a monolayer CVD MOS2 device. As you see, the fit is relatively good. It turns out that the internal resistance between these two faces is as low as 75 ohm micrometer. That's, as I said, we have a junctionless, seamless contact, and the metallic face has a relatively low work function, so that forms a very good ohmic contact to the semiconducting one. But of course, still we have the external contact resistance between MOS2 and metal, which is about 500 in the single layer and about 600 in the tri-layer MOS2. Velocity is more or less the same, about 10 to 6 centimeter per second. And as expected, the exfoliated tri-layer MOS2 has a larger mobility of about 25 square centimeter per volt second compared to 8 square centimeter per volt second in the monolayer MOS2. So now that we have all these intrinsic and resistance parameters, we can plug them in again back in the same model to predict the performance of a single transistor. What we have now is a chain of transistors. It helps us to see the performance of these channels at this channel length regime. But eventually, we want to build single transistors. So we already can predict the performance in a optimized device structure. So this is a monolayer and tri-layer. As you see, in both cases, we have very good subthreshold characteristic. If we also scale down the oxide to 0.7 nanometer, which is the state of the art now in the industry, and very low off current, relatively high on current. These set of parameters are very close to the ITRS roadmap requirement for technology node of 3.5 nanometer, which has a channel length of about 7 nanometer. So next, I just want very quickly talk about power scaling. What we saw already is just about channel length scaling, but at the same time, we should think about power scaling, which is these days very important. We are making the transistor smaller. The subthreshold swing is increasing, which means that we need higher supply voltage to reach to the minimum of current. The problem here is that we have already reached to the limit, because in the MOSFET structure, the subthreshold region is limited to 60 millivolt per decade. And as you can see here, the supply voltage is already saturated. About nowadays, I think it's about 0.7 volt, and also the threshold voltage. So to lower the subthreshold, to basically lower the supply voltage, we basically need to make the subthreshold swing steeper. And that's not possible with MOSFET structures, because this 60 millivolt per decade is defined by the device physics. We need a different device concept. Right now, the most practical device structure is TFET, tunneling, band-to-band tunneling transistor. In this devices, basically the carriers are tunneling through the barrier rather than jumping over the barrier by thermal emission, so that theoretically, the subthreshold swing is not limited to 60 millivolt per decade, and it can be much steeper than that. However, we should be careful that the device performance can be easily affected by the interface. Any defects at the interface can induce extra current, trop-assisted tunneling current, so that would increase the off current in the device. please.
Why was it? Because the 60 number comes from room temperature.
It's from room temperature. It's basically it's a thermal voltage, so it's K2 over Q.
Yeah.
Yeah.
And but the thermodynamics is still there on the right. So how do you get rid of room temperature?
This one, well, because there we have the here it's not limited to the tail of the Fermi level, basically.
Oh, you're coming out of the middle.
Yep. Yeah, we don't need to vary the barriers, just tunneling through it. So to switch off the device, we basically need to move this part up, so the carriers here don't see the band the other side.
And then you're using the band edge.
Yeah, we are basically using the gate to move the band here. So when it is high, then the carriers cannot tunnel through it. That's the sharp edge. Fine. So yeah, I mean, we need a very sharp edge. So that's why that the interface is very important here, and it can basically easily destroy the subthreshold characteristics of the device. And that's actually why that, well, although it's a very beautiful idea and device concept, in theory, in experiment, TFET doesn't really work. I mean, all the TFET structures so far, experimental results, have subthreshold swing above 60 millivolt per decade. There is no real experimental data that is showing a sub 60 millivolt. Everything is just simulation and modeling. So that's why we believe that the heterojunction, the van der Waals heterostructures with layer crystal can potentially solve this problem. Because here, the advantage is that we don't have, we actually have a very sharp interface. We don't have defects or dangling bonds on the interface. So that's technically it's very clean, and that can basically solve this problem. So we tried a simple example. We tried a tungsten selenide molybdenum disulfide device. It's a PN junction. So MOS2 is N-type, and tungsten selenide is typically a P-type semiconductor. So we can build Isaki diode or tunnel diode. And the device works very well. Actually, we have a very strong NDR region here in the forward bias, which indicates a strong tunneling process. And in the reverse, where we have band-to-band tunneling, actually we have a very steep conductance with a slope of 75 millivolt per decade and a curvature factor of 62. So the device is working very well. We are working on it right now to build the TFET transistors. But we also saw something very interesting in the transfer characteristics of the device. Actually, we see something similar. We have this peak with a peak to value more than 10 in the transconductance. So it's a negative transconductance or sine chaining transconductance. Here you can compare it with a regular MOS2 transistor. The black one is the heterostructure. So we thought about it, how to use it, and develop a device idea based on that. We came up with the inverter idea. Inverter are a very important building block in logics. So they basically flip the input logic. If it is 0, you have 1, and if 1, you have 0. But using this extra feature here, we can design a ternary inverter where we have an extra state in between. So on the same footprint, on the same device area, we have a large inverter device with an extra logic stage. So that's more or less what I want to talk about it today. If you have any question, I would be very happy to answer.
Thank you very much. Questions?
Two questions. One says that in 2D material, I guess you won't dope your material like we did in semiconductor, right? And how do you increase in conventional semiconductor you dope?
You mean you implement doping?
Right. And in 2D
here, normally doping is by surface treatment. So you still need to dope it, but you don't need to implement ions or dopant inside the crystal. That would destroy the crystal, especially if you're working with a monolayer. But since they're very thin, you can basically put down the dopant layer right on the surface, and that would dope the system. It's all based on surface modification.
Sorry. The other question is about the mobility. I remember you showed one slide about mobility. And do you understand what makes the give you the mobility? Generally, in semiconductor, in silicon, the mobility have two main mechanisms. One is phonon, the other is disorder scattering. But in the 2D material, do you have some understanding?
We actually have the same thing here, plus interface AC, because they're very thin. They can be easily affected by the trop charge at the interface, by defects at the interface with the oxide. Also, if you are using high dielectric material, where you have soft phonons, it can also lower the mobility.
I understand why the silicon curve is very steep with the as function of a channel length. Why with 2D material does not?
Because here, the point here is that in bulk semiconductor, the dominant process is not the phonon, is the dangling bond at the surface. So when you make it very thin, you don't have any more enough bulk states. Everything is right on the surface. And at the surface, you have unsaturated or dangling bonds. There are scattering sites so that would dominate the transport. But in 2D material, in a perfect 2D crystal, you don't have dangling bond on the surface. So that's why it's less sensitive to thickness.
Can I ask a technical question?
Sure.
So how do you define the gallium oxide of the
Normally use 80. Yeah.
2D material, it's not easy to grow a uniform pattern.
Depends what 2D material. For example, on graphene, no, you cannot, because it's very inert. But on molybdenum disulfide, well, you need to vary with the temperature. At some temperature, it works. Because molybdenum disulfide in general is hydrophilic. So if you start ALD at low temperature, you can nucleate the first layer. And then for high quality ALD, you can go to higher temperature. If you start at high temperature, water would not sit on MOS2. Yeah, you just need to play around with temperature. Normally, you start with low and then go to high temperature.
Can you comment on the frequency response, or cutoff frequency of these MOS2 transistors?
You mean for RF application? We have not worked on it, but I have seen some nice work that they have got cutoff frequency to gigahertz. But you need very short channel devices.
So Professor Jinkong's group published a paper. I think they have fabricated graphene and MOS2 lateral heterojunction. And do you know their work, and how do you compare the device with your lateral?
Well, that's a very interesting idea. And that works very well. But right now, the contact resistance is relatively high. We need to figure out what's the origin of that contact resistance. Yeah, but in general, yeah, that's an idea. You're basically stitching graphene to MOS2.
For these particular devices, are you using exfoliated films or are you doing QD?
Both.
What works best?
The advantage of CVD is that it's larger scale. So you like it. You can fabricate more devices, but the quality-wise, exfoliated one is definitely better. So yeah, if you want to have a state-of-the-art device, you work it on, you use exfoliated one.
Trying to make low energy, electronics and switches in a millivolt or whatnot, and going after these tunneling. But they didn't have very much luck, and it's sort of like the graph that showed where they weren't getting a steeper slope. Do you know what the problem is, or is it just sort of a sorted dirt, or why can't?
Well, if it is a tunneling-based device, then again, we have. Is it tunneling?
Yeah, but the luck was not good.
Well, normally in tunneling we have this trap-assisted tunneling that basically increase the subthreshold swing. So you always have some background current, which is not modulated by the gate. So where the channel is supposed to be off, you have some defects at the interface that help carriers to tunnel through the barrier.
And then the tunneling sort of goes away.
Yeah.
And yours, the interface with the moly disulfide is sort of unusually clean, or at least you know what you're doing, so you put it together.
With the tungsten selenide, you mean?
No, what you just did.
You mean in the heterostructure?
Yeah, because then you get this very 75 millivolt.
Yeah, well, we work on the transferring technique, make sure that the interface is very clean, and normally you have air bubbles between. So we need to somehow iron it to remove those bubbles, because there are, I mean, if we have bubbles trapped between, that also is an extra barrier. Well, normally people use a tip of AFM to soften it, to remove it. Yeah, it's and also annealing always helps. After the transfer, we anneal it at very high temperature. That helps to improve the adhesion.
Does it help to make the device very small, because then you can get lucky and find a good spot that works?
Of course.
One last question. I guess this is more of a generic question. I mean, if I talk to people in the semiconductor industry, I mean, what are they thinking? Are they thinking 2D materials, or are they thinking just trying to go to 3D device structures with conventional materials?
Well, you know, I mean, they have developed technology based on silicon for more than 50 years. So it's very hard for them to, to switch to a different platform. But at some point they have to. They already, I mean, we believe that next two generation would be based on 35. Or at least there would be some 35 integrated with silicon. But do they believe it right now? No. We first need to show really high quality material, high quality devices. And right now, the biggest problem, the main bottleneck, is that we don't have larger scale, high quality, something comparable with silicon. Yeah.
Okay, any last question? Well, if not, let's thank him again.